In this video, I'll talk through examples 2.4, 2.5, and 2.6. Now, the big thing that's going on with these examples, what are they examples of, is set builder notation. So the book doesn't call it this, but this is commonly known as set builder notation. So I'll introduce that, set builder notation. And the idea here is that we can build sets from an open sentence. So let P of X be an open sentence over some domain S, so with X in some other set. What we do is we can collect all the elements of S, for which this open sentence is defined, that satisfy P of X. And so we write that as follows. We say it's the set of all X. We could say X and S if it's not clear. Here it's clear. So it's the set of all X such that P of X. So that is, this collects all X in S such that P of X is true. So let's look at an example of the set builder notation. Example 2.4, we see that A is the set of all n in the n in the integers, such that, and this is how this is read, this little colon here is read as such that n squared is less than or equal to 4. So again, so what is this set? It's the set of all integers that satisfy this open sentence. So collect all the integers that satisfy this open sentence, and that's what the set A is. So in particular, for which values of n is n squared less than or equal to 4? This is a problem like we did last week, where I want to find all n that make an open sentence true. And that's partly why we did that, was to be able to use set builder notation more easily, to have had practice with that. So again, we're collecting all n for which n squared is less than or equal to 4. So that means, right, it must be that n is -2, -1, 0, 1, or 2, all make that statement, that open sentence true. Or these all make the open sentence into a statement, which is true. And so these are the elements of A. We could also write this, if we want, we could write this again using a different variation of set builder. In general, there's lots of ways to describe a set, the same set using set builder. I could say this is the set of all n in the integers, such that -2 is less than or equal to n is less than or equal to 2. That's another way to describe the set, again using set builder. So we could list the elements, or we could describe it here. When we're dealing with very big sets or infinite sets, you'll see that we use set builder notation quite a bit, because that's the easiest way to describe sets like that. So that's how set builder notation works. Let's look at a couple other examples of this. Take the set A, which is the set of all real numbers. Again, pay attention to how I read the set builder notation. The set of all real numbers such that x squared minus x minus 6 is equal to 0. So again, we're collecting all the real numbers this time, for which this polynomial is equal to 0. Well, factoring this, if I want, I could rewrite this. I could change around my open sentence here, rewrite this. This is what? X minus 3, x plus 2 is equal to 0. And then it's easier to figure out what x values make this open sentence true. Here it's x equals 3 and x equals -2. So this is the set -3. Oh, sorry, x equals 3 and x equal -2. So it's this set containing these two elements, 3 and -2. In another example, we'll take a look at B, which is the set, again, of all real numbers for which, or such that, x squared plus 1 is equal to 0. So think about this one for a second. Which real numbers satisfy this? And you should recall that no matter if x is positive or negative, if I square it, that'll always be greater than or equal to 0. So that implies that x squared plus 1 is greater than or equal to 1, which is strictly greater than 0. So x squared plus 1 is always strictly greater than 0. In particular, it's never equal to 0. So there are no real numbers that satisfy this. So what set is B? It's the empty set. It's the set containing no elements. I think at the beginning I said 2.5 and 2.6. There is no example 2.6. I lumped those last two examples, or I split them up when I shouldn't have. So 2.4 and 2.5. All right. That's it for this one.